me again. So this second talk is about MadIPM. So maybe some of you are aware of MadNLP. So it was more or less one of the first solver, and during the last 5 years, we developed MadNLP, which is a nonlinear optimization solver on GPU. And recently, a lot of people were working on the LP with PDLP, for the first order, and we said we have almost all the bricks to do LP, so to implement second order method for LP. We just need to simplify MadNLP, and that's what we did for MadIPM. And we can see that we can specialize some kernel to expose the LP structure and potentially convex QP, and it leads a nice speed up. So we explain what we did and also where we are going, which means batch LP. And that's the initial goal of MadIPM, is to solve batch problem on GPU. So our team is composed of François Chengo and Mihai. So this is more or less the main team that developed the Mad suite. And of course, we have a bunch of colleagues like Michael, Dominic, and other contributors that works on this software with us. So today I will mostly focus on MadIPM. If you stay for RSNZ, I will give a talk on all the Mad suite on Friday. But this is a different component that we have. So we go from the linear solver to the modeling and the optimization solver in the middle. So we have a bunch of packages. And our three main solver are MadNLP, the nonlinear optimization solver. Michael will talk about after me about MadNCL, so I will not give too much detail about it. And what I will present now is MadIPM, which is a specialized version of MadNLP for LP and convex QP, which rely on Merotra predictor corrector method. So in terms of algorithm, I will not go too much into details. It's very classic in the sense that we have a LP problem, we have the Lagrangian, we do the KKT condition, and with the Newton method, we want to solve this nonlinear system of equation. And from that, we need to solve a bunch of linear systems which have this structure, and with the Merotra predictor corrector, we have the advantage to solve two systems per iteration with the same factorization. So we gain time compared to the NLP case because we have the same left-hand side for the system, so we don't need to perform again a factorization. We can reuse it with a different right-hand side. So we solve these systems, but these systems are non-symmetric, and for being more efficient, we eliminate subblocks. So in general, we eliminate the XL and XU blocks, and recover the quite common augmented system, which we solve quite often. And potentially, if we eliminate the 1-1 block and do the short complement, we cover the normal equation. Now, what can we do to solve the system on GPU? So on GPU, we want to use an LDL and not an LBL, and it's important for accuracy to do that, or Cholesky on the normal equation. But we'll see that we'll have some issue on GPU to form the short complement, and also explain why we only right now rely on the augmented system. So we want to target these two systems, but what are the limitations on the GPU? And on GPU, as you know, we can have these different issues. If you have free variable, we need to be careful and handle them, otherwise a 1-1 block is degenerate, is singular. If we have redundant constraint, we need to do preprocessing on A, so we need to be careful on that also. If we have any dense row in A, our short complement will be totally dense, so we need to be careful and use potentially the Sherman-Morrison trick to handle it. And all these things are potentially hard to implement on GPU. That's additional layer that is state-of-the-art on CPU, but on GPU it's harder to implement. And because of all these tricks, tricks needed to solve efficiently the short complement, we prefer to stay on the augmented system. The issue with the augmented system is if we want to solve this 2x2 block system, we need what we call a Duff-Reid factorization, an LBL factorization. And this kind of factorization is what we have in HSL MA57, MA27, MEMS, Espiral, Paradiso. But we don't have that on GPU. On GPU, we don't have this kind of factorization. We only have what we call LDL, which is a signed Cholesky. And this thing is very important because it will lead to potentially an impossibility to factorize your system. So if you apply directly QDSS or any signed Cholesky on the 2x2 system like this, you can, even if the matrix is non-singular, encounter at any moment a null pivot. And potentially, depending on the ordering returned by Metis or on other tools to minimize the filling of the factor, you have no guarantee that your factorization will not fail, even if non-singular. And it's super important to be aware of that when you develop an optimization solver on GPU. And one kind of system that is very important, another important class of linear system that we have is what we call the symmetric quasi-definite system. And this symmetric quasi-definite system is something in the middle between symmetric positive definite system and indefinite system. So you can ask, what is a symmetric quasi-definite system? Is these kind of things. And if you have a 2x2 block system where the 1-1 block is positive definite and the 2-2 block is negative definite, or any symmetric permutation of a matrix can allow to recover the structure, it's called a cis-QD system. And this cis-QD system, whatever permutation you apply on it, always have an LDL factorization, a signed Cholesky. So we are sure to be able to factorize it with an LDL, which is what we have right now only on GPU. And if you ask, will in the future LBL factorization will be available? Maybe, but even if it's available, it will be slower, because when you have an LBL, you need potentially to do reallocation of the buffer to perform the factorization, and all these things are a cost, and it will lead to a slowdown on GPU. So potentially, right now, it makes sense to adapt our optimization solver to be careful on the algebra aspect to make it more GPU friendly. So what we did is we add a primal and dual regularization, so rho and delta parameter, to ensure that we can always factorize the system with QDSS. And even on CPU, if you do that, you have an option in MA57, for example, to say, I don't want to do any pivoting because I'm sure that is not needed. And you can give a nice speed up already on CPU if you do that. That's something important, as I said, when you implement your linear system. So this is the key, and we factorize this thing with the LDL of QDSS. So what is the gain now? So I have a graphic, and for highs, it was before the release 1.12. So it was without EPO. So be aware of that. Even if the performance is not good, it was before with IPX when we did the comparison. So what we can see here is for the comparison, it's always very hard to benchmark solver between each other. And here, for example, if we use A30 or H100, we have a very big gap of performance on GPU. And if you use one of 16 thread for the Cholesky of Groby, we also have a big difference. So it means that it highly depends on the architecture and a different CPU, GPU. But if we try to use the best Groby version and the best MadIPM version with a very recent GPU, we can see that MadIPM is a bit faster or match Groby performances when you use GPU. So this was the first benchmark. The second benchmark is on only a subset of the problem, so more or less the one that requires the biggest amount of time to be solved. And we here only compare MadIPM with H100 and Groby with 1 or 16 thread. And of course, that's the key point of this slide is problem dependent. If you use GPU, it doesn't mean that you will have a speed up. It depends a lot on the problem and the architecture. But you can see that for the biggest problem in practice, we have a nice speed up by using the GPU in MadIPM. So this is what we have right now. And if you want to solve it with JuMP, on CPU, I have a very simple LP problem. And if you want to solve it on GPU, you just need to add an option that we more or less move all the data, all the LP or convex QP problem directly to the GPU, and we'll use QDSS as a solver. So it will be almost no modification, and you can solve all your LP on GPU this way. And this is possible here because we don't need any automatic differentiation. If we want to do NLP, that's another problem, but without it, it's quite easy to potentially solve the problem on GPU with JuMP. What do we want to do in the future, and what are also currently the key tricks that we use for making the implementation fast. The first one is what you need in the LP solver is after you did the factorization is to do a bunch of product with the Jacobian. And to do that efficiently on GPU, you need to be aware that doing a matrix vector product on GPU require more than doing just a for loop. In GPU, you need 3 steps when you do a sparse matrix vector product. First, you do an analysis, a little bit like a factorization, an analysis of the sparsity pattern of the sparse matrix. And CUDA or ROCm, for depending on your GPU vendor, will do an analysis of the sparsity pattern to derive a load balancing to have the most efficient matrix vector product. And these things take around 20 or 25% of the time. And if you're not careful, every time that you do a new matrix vector product, you will do against this analysis or nothing. Because here, the Jacobian will not change. And even if in the nonlinear case, you will still keep the same sparsity pattern. So it makes sense to store the analysis of the sparsity pattern and reuse it at each step. And also, compared to CPU, when you do matrix vector product on GPU, you need to be aware that you need an additional buffer compared to CPU. And this buffer, you don't want to deallocate it. On GPU, it's also way more expensive to allocate and deallocate memory. So that makes sense also to be careful and keep this buffer and reuse it at each step. So we did operator, which is very similar to what I use for Quillov preconditioner, but here it's directly embedded in MadIPM. And when we need to do product, we already have an operator specialized and reuse all the information. So that was the first thing that helped to have good performance on GPU. The second one is after we compute the descent direction, we need to do a fraction to boundary line search. And compared to what we have on CPU, we adapted a little bit such that we can easily use a map reduce operation, which is more GPU friendly. So we didn't do. Okay. So we didn't did so much modification, but we adapted a little bit the code to be more GPU friendly, and it also impacted the performance. So be aware that just even a line search can be harder to put on GPU if you use the pure CPU version that we have right now. So as I explained before, porting a code to GPU needs sometimes a redesign of the optimization solver and different aspects. And the last thing that is important and quite often hidden in the benchmarks is when you want to solve big LP and big QP, you have a pre-processing phase, which sometimes almost solves the problem. And pre-processing, many steps are not GPU friendly. And here, we still apply it on CPU. And I think some components can be ported to GPU, but many of them will still be CPU, or will be still done on CPU. So this is the current version of MadIPM. What do we want to do in the future? What we want to do in the future is to do batch. But before that, a last comment about the show complement. So as I explained before, we have 2 options to solve the system in MadIPM. Or we rely on the 2x2 block system, which we call the augmented system, or we go to the show complement. And the show complement have a few issues. One of them is potentially if you have a dense column, all the show complement will be dense. So you need to do pre-processing to check that, but pre-processing is only CPU friendly. And also building this A time diagonal time A transpose matrix is more or less a sparse times sparse product, and also it's quite hard to make it GPU friendly. So it requires a lot of work to have efficient GPU kernel to do this product. So that's why for now we don't rely on the normal equation. And also something that we need to be careful, and we would like to work more on it, is a few years ago Michael developed a formulation where he scaled this way the 2x2 augmented system. And this kind of scaling is on CPU done in the solver, like Paradiso, ME57, ME27. They do all this scaling for you when you call the solver. On cuDSS, this scaling has an additional cost, and more or less all these operations are not done. So that's why it's way less accurate to solve linear system on GPU right now with the sparse direct solver. And we need to be careful of that and do more or less the scaling on our own. And this trick helps a lot the cuDSS after. So I mean the accuracy of the descent direction, this delta x tilde and delta y is way more accurate when we rescale the system. So this is called the K2.5 formulation. You can check the paper of Michael about that. And potentially we are wondering if one day we go to the show complement, can we use something similar where we use the show complement on this system to be more accurate? So that's an open question. Nobody investigated before the Schur complement with the scaling for the 1-1 block system. And as I said, the next step are going to batch. So the advantage to do batch is potentially if we just change some parameter in the LP problem, we still have the same KKT structure. And if we have the same KKT structure, so the same structure, the same sparsity pattern for this 2x2 blocks, so for this 2x2 block system, we can only apply the ordering once. And when we solve sparse linear systems, which take almost 70% of the time in an enter-open method, we want to be efficient for the three phases, which include the symbolic analysis, the numerical factorization, and the back solve, the triangular solve at the end. And the first component, the analysis, right now is a bottleneck because it's mostly CPU. It's Metis inside, and nobody will implement Metis on GPU. And if we can batch the system, we can only do the ordering only on one system, and we use them for all the batches. So we will lead a nice speed up. More or less, we will have the ordering for free for the other problems. And it will be also, by nature, it will create a SIMD code for us. So single instruction, multiple data, we create it naturally with the batch. The open question is, what do we do in terms of API? How do we potentially use the parameter in MOI to evaluate in parallel the objective, the gradient, the non-zero of the Jacobian, and the relation of the Lagrangian? It's an open question. I don't have the answer for that. And in terms of application, we, for example, at the DCOPF, where it makes sense potentially to solve a batch of LP where we have different load. And the last question is, if we solve a batch of LP, potentially the convergence can be different because they have a different central path. And because of that, some system can converge faster than another one. And what can we do in that case? Do we do, we compute on the fly a load balancing to move the parallelism somewhere else? That's an open question. And to conclude about this presentation, we are working on this batch with two colleagues from Georgia Tech, Michael Klamling and Andrew Rosenberg. And we hope that by being able to do batch IPM will help us in the future to batch MadNLP and MadNCL, which will open a new question, how we do batch AD. But I think that makes sense for example, an energy problem where we need to solve ACOPF with different load in parallel.
Thank you.
Thank you.